This is everything you need to know about trigonometry at a basic level. By the end of this video, you should be confident in your knowledge on this subject. If you like the video, make sure to hit that like and subscribe button. You may be wondering, what the heck is this stuff? Like, what does this even mean? Well, today I'm going to explain that. So, why is this stuff important? Why is trigonometry important? Well, when you're given say a triangle, we're given some angle, we'll say theta, and then maybe some other side length, like this side, we'll call it x. Given only this length here, and this angle, you can determine the length of this side, y, or this side, z. Now, I'll show you how. First, we have to start off with what is sine, cosine, and tangent. So sine of theta is equal to opposite over hypotenuse. Cosine theta equals adjacent over hypotenuse. And tangent theta equals opposite over adjacent. Now, what does opposite, adjacent, and hypotenuse mean? Well, basically, when we draw our triangle and we have our angle in this corner here, we have three sides. We have this side, and this side. Well, our hypotenuse is this long line that's on an angle. Adjacent is the side that is adjacent to our angle, and opposite is the side opposite to our angle. Okay? So it's that simple. So say we have sine of theta. What that really is equivalent to is this ratio between opposite and hypotenuse. Okay? So this can be really useful. It can be very helpful to find these distances or measurements. But there are a few more trig functions that could help us out. These are cosecant, secant, and cotangent. Now, these may be like, we already have all this stuff. Why do we got more? Well, this one is just 1 over sine. This one is 1 over cosine. And this one is 1 over tangent. It's really that simple. So these could come useful in other problems, other applications. Another relationship I want to highlight is tangent theta is really just sine theta over cosine theta, which means that cotangent theta is equal to cosine theta over sine theta. Okay. So really, all of this stuff, there may look like there's a lot of stuff here, but it's really just composed of sine and cosine. That's it. Sine and cosine. Tangent is sine over cosine. Cosecant is just 1 over sine. Secant is 1 over cosine. And cotangent is just cosine over sine. So these two are the basis for all the rest of this stuff. Now, let's move on to, now we know how to solve for the dimensions of the triangle, but what about the angle? Say we're given a triangle, we have some unknown angle, and we're given these sides, x and y, or adjacent and opposite. So we don't know what theta is, but we do know what x and y are. Well, we have two trig functions we could use here. We could use tangent, which is opposite over adjacent, or we could use cotangent, which is adjacent over opposite. It's up for you to choose. I'm going to choose tangent. So if you say tangent theta equals opposite over adjacent, which means that tangent theta equals y over x. But we're trying to solve for theta. Now, how do we do that? Well, we can't just divide tangent to the other side. That's not really how trig functions work. But we can take the inverse tangent of both sides. So if we do that, it's commonly known as arctangent. So if I take the arctangent of tangent theta and the arctangent of y over x, well, this arctangent is going to cancel out this tangent. So really, we're just getting theta equals arctangent of y over x. And this is how we solve for theta, our angle. Arctangent just means inverse tangent. And it's a special, it's kind of the exact opposite of tangent. So normally we would plug theta into tangent to get some distance or ratio of distances. Well, arctangent works the other way around. We plug in an angle, or we plug in distances, and we get out an angle. Okay, so now we got that down. While on the topic of angles, we have two different kinds of measurements of angles. We have degrees and radians. Now, degrees are self-explanatory. We have, say, 90 degrees, 180 degrees, or 360 degrees, right? These are all very common angles. You probably know a general idea of what they mean. This is, say, like this sort of deal, like 90 degrees, a right angle. 180 degrees would be something like this, like you spin all the way around, and then 360 degrees would be something like this, where you spin all the way around and come back to where you originally started. Now, from degrees to radians, if we take the degrees, say 90 degrees, and we multiply by pi over 180, this is our conversion factor, so we have pi radians over 180 degrees. Our degrees are going to cancel out. What we're left with, 90 over 180, that's just going to be 1/2. We're left with pi over 2 radians. Now, radians are dimensionless. It's just an angle. They're very useful because they are dimensionless. So if I do this conversion factor, you can do this for any degree and convert it into radians. If I do this, 90 degrees is going to be pi over 2 radians. 180 degrees is going to be pi radians. And 360 degrees is going to be 2 pi. Sorry, that 2 was terrible. 2 pi radians. Okay. And if we want to go from radians to degrees, we just have to do this, but in reverse. So let's try that. Say I have pi over 2 radians. I'm going to multiply by 180 degrees over pi radians. Right? Our radians are going to kind of cancel out. What we're left with, this pi and this pi go away, we're left with 90 degrees. Right? 180 over 2. Makes sense? So you could use either. More commonly in calculus, you'll find radians. They actually come up a lot more in calculus, and I feel are much more useful in that sense. So now we got all that stuff out of the way. We got our trig functions, we got our inverse trig functions, we got our radians and degrees. Now we can apply some identities to these trig functions to solve complex calculus problems that you may have seen in previous videos. So a very common identity is sine squared theta plus cosine squared theta equals 1. This is a very common identity. It comes from Pythagorean theorem, which is a squared plus b squared is equal to c squared. Well, using this basic Pythagorean identity, we can come up with more identities for other trig functions. So let's start off with dividing this by cosine squared theta. Now if we do that, we're going to get sine squared theta over cosine squared theta, which is just equal to tangent squared theta, plus cosine squared theta over cosine squared theta, which equals 1, equals 1 over cosine squared theta is equal to secant squared theta. And this is another identity that we can use that relates tangent and secant together. Well, let's go back to our original identity. But what if we divide both sides by sine squared theta? Well, sine squared theta over sine squared theta is 1, plus cosine squared theta over sine squared theta is cotangent squared theta. 1 over sine squared theta is cosecant squared theta. And here's another identity. So we have this one, which relates cotangent and cosecant together. This one, which relates tangent and secant together. And this original one that relates sine and cosine together. And these can be very useful when dealing with squared trig functions or any higher power trig functions. It can come into play with a lot of trigonometric integrals or derivatives or any algebra needed for trig functions in general. So let's move on to another set of trig functions. These are known as the double angle, or, well, sometimes they're known as half angle identities, which involves when we're looking at just one square trig function, we can relate it to a double angle of cosine. Now, this can be very useful for solving integrals. Another one we have is cosine squared theta, which is very similar, 1 plus cosine of 2 theta. Again, very helpful. And a final one for tangent, with 1 minus cosine 2 theta over 1 plus cosine 2 theta, which, if you notice, is really just this over this. Right? The 2 would cancel out in that case, and we're left with just this. Pretty cool, huh? And you could relate this to the other, like cosecant, secant, and cotangent, the other trig functions, and play around with it. And I'm sure you can figure out how that could be helpful. And one last set of important identities is the double angle identities. So when we have our trig functions with these doubled angles inside, we can actually relate this to some single angles. Okay, this can be very helpful when evaluating functions, especially if we not necessarily know what our theta is. We can kind of get into an easier form here. Same thing with cosine. We have cosine squared theta minus sine squared theta. Again, used for a lot of identities, algebra and solving equations. This cosine 2 theta also, if you rearrange it, equals 2 cosine theta minus 1. From here to here kind of uses our Pythagorean identities of sine squared theta plus cosine squared theta equals 1. We can kind of rearrange some stuff, noting that sine squared theta is really cosine squared theta plus, 1 minus cosine squared theta. That's what that would be. And also you can represent this just in terms of sine in the same way by saying this is 1 minus 2 sine squared theta. Okay. And one last one, tangent. We have 2 tangent theta over 1 minus tangent squared theta. This one is a lot more uncommon. It's not used nearly as much, but it still could be useful. One last thing with these trig functions is they're even and odd identities. So when we have sine of some negative angle, say, well, since sine is technically an odd function, this will equal negative sine of regular theta. Okay? But the same is not true for cosine. If we have cosine of some negative angle, cosine is an even function, therefore this will be the same value as cosine of normal theta. And for tangent, well, tangent is an odd function, therefore it'll be negative of its original value. Same thing with cosecant. Since cosecant is related to sine, we're going to get the same sort of identity, same sort of relationship, as well as cotangent. This is also going to be negative cotangent theta of regular theta. And since secant is related to cosine, it too shares the same quality as cosine and just becomes positive. Okay? Now there's a whole another theory about positive and negative angles for, or rather, even and odd functions in calculus. There's a whole topic on that stuff. But thank you so much for watching. If you enjoyed this video, make sure to hit that like and subscribe button, and leave a comment below of what topic you'd like to see next. This is Dylan signing off. Hope you have a good day, and see you in the next one.